so thank you very much for the invitation. Thank you very much for the introduction. Usually I'm a seismologist, and usually I give talks to other seismologists. So coastal management is something that is not common for me. But actually it's, I would say, very much related, because usually coastal management is, people think about what's happening at the surface, and with seismology, it will give us the opportunity to look and understand what's happening beneath the surface, underneath our feet. And in the case for Malta, and probably most countries, the most important resource is groundwater. Now, the case for Malta is particular because it's a very small island. This project is funded by the Energy Water Agency, which is the national agency in Malta. And because this is a very important resource, basically half of the water that is available for potable water for drinking comes from the groundwater, and the other half comes from desalination process and plants, which are along the coast, and they consume a lot of energy. So there's an impact related to the environment. So understanding and managing our resources is very, very important. But first we need to have the tools to do the monitoring. I would like to mention Luca Laudi, which is a master's student. He's right now finishing his thesis. I will be showing also results from his work. And the PI is also co-PIs Polingali and Sebastiano D'Amico. And today I will be showing, I hope, very nice results. And I hope I will convince you that the technique is a very, very nice technique, and that it works. Okay. So here's a short video, just a quick introduction, but if you cannot hear or miss some parts, I will be talking about this project. Okay. All right. So that's a promo video. I will be talking a little bit about the technique. I hope I don't scare you off about the science a week before Christmas or 2 weeks before Christmas. But my take-home message would be that there are new tools, seismic tools, to actually that we can use to monitor groundwater. So what's the situation? This is the island of Malta. It's very small. It's probably one of the smallest, or the smallest state in the European Union. The climate is semi-arid, with very limited rainfall of 500 millimeters. Unlike most countries in Europe, we don't have any lakes, we don't have any rivers. And then we have a very high population density, topped up with a very high density of tourism. Just to give you the numbers, the population is about 500,000, and then we get 2 million tourists. So the demand for water, especially during the summertime, is very high. Therefore it's of importance that we understand the water system and find the tools necessary to improve our monitoring. Here's a geology map of the island of Malta. What I would like to highlight from this map is that there are these 5 layers, which you see on the top right. And we will be looking at the lower coralline limestone, which is at the very bottom. But there's an interesting geology from the northwestern part to the southeast. And this in the future will require further studies because it has its own hydrological system. But today I will be talking about the lowest aquifer, which is within the lower layer. For those who are not familiar with the process, hydrological process, this is a cross section. So this is the previous map, and this is a cross section from southwest to the northeast, where basically you have these 5 layers. You have the infiltration from rain, precipitation, when it rains, and then it goes into the water system. In Malta, we have a very good network of boreholes, which are run by the Energy Water Agency, the Water Service Corporation, private companies as well. We have a system of galleries. These are close to the mean sea level. Some of them go back in several decades. So the water problem has been identified for many years now, especially when Malta was a military island. And these were developed to extract the freshwater resource. And what's interesting in this figure is that you have these lenses where you have groundwater, and then you have seawater, and you have the interaction between the two. And you have the groundwater, you can see it rising and going down again close to the borehole. So basically, when I'm comparing with the borehole data, I will be comparing with the mean sea level. So this is the mean sea level, and in some places it is higher than expected, and it's because there's more groundwater. So this is a general schematic of the hydrology system in Malta. Going to the seismic part, in Malta we have the Malta Seismic Network, which are the red triangles. And it happened that between 2017 and 2018, we had a temporary seismic network, which are the orange triangles. And this gives us a nice opportunity to do the analysis across the island using so many stations across the island. So considering the small size of the island, this is quite a high resolution network for the size of the island. But in generally, the network are the red stations, which is the permanent seismic network. Because of this, we had for this experiment, we had 2 types of stations. One is what we call broadband. Basically, they are very broad in the frequency range that they can sample. This is a typical setup for such an instrument. You have the seismometer over there, and the electronics set up in a room. And these make up the National Seismic Network, which are the red one. And then we have in this case, we have these simple, more basic instruments and setups where these were deployed for the temporary network. I'm highlighting this because part of the experiment was what type of instruments are able to detect the groundwater. These type of instruments and setup costs a couple of thousands, like about 15,000–20,000 to set up, whereas these ones are much cheaper, less than 5,000 euro, and they are easily deployable. So if you want an instrument somewhere, you find a quiet place, you need the electricity and a place where to leave it quiet, and that's it. So part of the experiment was to also compare these 2 types of instruments, whether we need sophisticated instruments or less sophisticated instruments. A little bit about seismology. This is a typical seismogram that we usually people see when there's an earthquake. And usually these instruments are used to detect earthquakes. And this is an earthquake waveform. So when there's an earthquake, seismologists look at this part of the waveform to analyze the earthquake. But in this study, we are actually looking at what we call ambient seismic noise. So basically, in between earthquakes, the instrument is still recording, and it's still recording the vibrations of the ground. And usually this type of data is disregarded, thought that it is not useful. But actually, the examples I'm going to show is making use of this ambient seismic noise, which actually there are signals in it. And so the question is, where does the signal come from? The signal for the ambient seismic noise are the vibrations in the ground, which are, we call them microseisms, and these are caused by the coupling of the ocean wave energy with the seafloor. So the sea is always moving, there are waves in the sea, and the waves are hitting the coast, are hitting the ocean floor, and these generate these what we call microseisms, and these are a signal. The signal is lost in this noise, is part of this noise, And the analysis that we do is basically using the frequencies related to the noise generated from the ocean waves. So basically, our source of energy is free. It's out there, especially we're a small island. We're surrounded by the sea, so we have a lot of the signal. And in this experiment, basically, we use the signal. We analyze this signal to understand what we can detect from this data. Okay, I promise you 2 or 3 slides of theory, but I try to keep it simple with cartoons without any equations. Okay, so imagine we have a seismic station here, the black triangle, and this is the rocks. And the rocks, they can be saturated with water or not saturated with water. So here, for example, where you see the blue, you have pores with water, saturated with water, and in this case, there's on top of it, there's no water. And we get what we call a parallelogram reference, which is a seismic signal for this environment. Let's assume it rains a lot, and so now the rocks are saturated with water. As you can see, the blue now is filling more the air pockets, and we get a slight shift in the signal in the parallelogram. So in the seismic signal, we get a slight shift. Or the other way around, a slight shift in a different way. If there's no water, if there's a drought and there's less water in the rocks, we get a slight shift in the signal. And the slight shift is in time. So this is why you see dt. So it's a reference in time to the reference signal that we have. And this technique is using just one station. We call this autocorrelation. In another method, okay, here are the examples. So pore pressure increases, the grain contact decreases, so the seismic wave speed decreases. Or in the other way, if the pore pressure decreases, then the grain contact, the contact in the rocks increases, which will then help to increase the seismic wave speed. In the other technique is what we call cross correlation. So in this example, we have 2 stations. So here we have detector 1 and detector 2. There's noise being recorded at this detector, and there's noise being detected in the other station. If we do a correlation is a mathematical function to tell us how similar the signals are. We get the correlation signal, the parallelogram reference. So the 2 techniques are either using one station or using 2 stations, where basically we take the data, the seismic data, and we correlate the signals to see how different they are from each other. And because there are these sea waves, the ocean waves hitting on the ground, then you have a very regular signal. And if it's recorded on one station, it should be recorded on the other station. So there is a signal common between the 2. And the correlation function gives us a mathematical, we call it impulse response, of how similar these signals are to each other. Okay, this is the seismic coverage. So before I show the seismic stations, which are the red and the orange ones, and if we are combining the 2 station methods, so we need 2 stations, then it gives us a lot of coverage because we are pairing the stations together from one station to the other, or the other station with the other. So this gives us a very nice coverage across the island. This is the data availability we have from 1995, and then in recent years, the network operation, more stations were added, so we have a lot of data in recent years. These are the parallelograms that I mentioned before, the difference between the 2. This is the reference parallelogram, and so we compare each day with this reference for each pair of station. Okay, and then there's some mathematical technique to compare the reference with the observed. What I want to highlight is that the difference is so small that they're actually on top of each other. And when we're talking about the delay time difference, the time difference between each one, we're talking about very small numbers, like 0.02. So it's a very weak signal, but it is a signal, it is there, and we can use it. And from time, we can then convert to velocity, assuming the crustal velocity in the rocks. Okay, let's go to the results. So what you're going to see here is a map on the top left. The blue, the orange triangle is the seismic station. IMSIDA is the one we have on campus next to my office right now. The green dot is the borehole data. So it's what you see here. And the blue dot is the meteor, the precipitation of when it rains. So basically, this graph is showing 3 things. The green is the borehole data, which you see here above the mean sea level, okay? The blue is the precipitation, how much it rains over the years. So the x-axis is the time over the years. And the red is what we measure, the bold red color is from the velocity changes that we detect from seismically. And what you can see, the blue shade is the winter time and the white is the summertime. So in winter, it rains a lot. The borehole data, you can see it increases. And in summer, there's less rain and the borehole level goes down. And if you look at the red data, which is the seismic data, is what's new, what we are providing, there's some very nice agreement between the winter and summer and winter. You can see there's some good agreement with the borehole data, especially if there are some peaks and the new oscillation. So I hope I can convince you that this technique is very, very good, and I'm going to show the next examples are different examples showing these. So note the seasonal variations with the winter blue shade and the summer in the next slides. Okay, this is another station. This is Schlendi seismic station. We have the borehole also in Gozo and the Meteor station on the island of Malta, and you can see similar patterns. So in winter the values go up, in summer the values go down as expected. So this is very, very exciting. In the station 4, the one we have in the south, the data goes back to 1995. So the borehole data that we have goes only up to 2016, but with this technique, we can actually go all the way to 1995. So we can look at the seismic record and look at the groundwater levels. These are some more examples to give you an idea that it works. I'm going to go fast forward basically in these examples. Here I'm using 2 stations. So this is the station in the south and the station in the north. And you can see the very nice pattern matching with a borehole located midway between the two. Keep in mind that the locations might not exactly agree kind of with the borehole because it might sample different areas, but the patterns are there. All right, I'll go fast forward here. Okay, so what's next? So we know this technique works. We can develop it further, especially in the future. We can look at the coverage. So here we can plot at different time and we can see the paths between the stations. So we get this national coverage. We can do techniques like seismic tomography. This is still work in progress, where basically we can find a mathematical model that fits all the paths across. And so this gives us a nice map changing over time, day by day, of the hydrology system in Malta. So this is work in progress. And we can also think of other techniques that can use seismic data to help us understand better the hydrology of the island. Okay, food for thought. So the stations that I showed are on land, but there's nothing holding us back except for funding to put stations in the ocean. So we assume that the fresh water is located onshore, but it would be interesting if there's fresh water beneath the sea, and it would be interesting if there is dynamics like changes, seasonal changes beneath the sea, because when it rains in the sea. So we don't know what happens then. So probably it's lost. Or maybe not. So it would be interesting to see if any link between the water that it rains on land going all the way, whether it's connected on sea. And this we can do by putting stations in the sea. Of course, we need funding for this. At least you need to leave the ocean bottom seismometers at least for 1 year. But it will increase the coverage substantially. So now it wouldn't just be on land, but actually we can extend further. For example, with 3 stations, if you put 5 stations, the coverage will increase further. We should consider putting a seismic station in the north of Gozo over here, because you can see we're missing a lot of information on this part of the island. So this is food for thought. I hope that the take-home message is there are new techniques. We should not also look at coastal management at the surface, but also understanding what happens beneath our feet, especially when it comes to resources. And there's opportunities to investigate offshore and link what is happening onshore with offshore as part of a coastal management system. All right, and these are my conclusions, and I would be happy to answer any questions that you might have after the next talk.